So the title is Fast Learning Requires Good Memory, a time-space lower bound for parity learning. So what is parity learning? In the problem of parity learning, we have an unknown x that was chosen randomly in 0, 1 to the n, a vector x of n variables. And a learner tries to learn x from samples, from a stream of samples, A1, B1, A2, B2, and where for every t, AT is just a random vector in 0, 1 to the n, and BT is the product of AT and X modulo 2. So basically you just get linear, I don't see. Okay, so basically you just get linear equations in the variables of x over GF2, modulo 2. And the learner has to learn x. There is very simple. There is no noise. It's just learning parities without noise. So this is the game. Are you all ready to play? Let's see if it works now. Okay, I'll use this. Okay, so are you all ready to play? So very simple. You only have to learn x1 to x5, but you really have to learn it. When in the end, you have to tell me what are x1 to x5. And I'm going to give you the linear equations. So first we have x1 plus x2 plus x4 plus x5 equals 0. No, don't write anything. It's a cheating. x2 plus 3 equals 0. x3 plus 4 plus 5 equals 0. 2 plus 3 plus 4 equals 0. 1 plus 2 plus 5 equals 0. 3 plus 4 equal 1. x2 plus x4 plus x5 equals 0. 1 plus 5 equals 1. x1 plus x2 plus x3 plus x4 equals 0. And x2 plus x3 plus x4 plus x5 equals 1. It's starting to be too boring, so I will not continue. Anyone knows the solution? What?
1, 0, 0, 1, 0.
No. Okay. Almost, but not.
Each try one.
Yeah, exactly. Okay, so basically there are two ways to do that. The first is by solving linear equations. And for that you only need O of n samples, actually n plus O of 1 samples. But the problem is that each sample contains n bits. You need n equations of n bits, so you need a memory of O of n square bits, a quadratic size memory. And the question is, what if you don't have a quadratic size memory? Can you still learn it? And of course the answer is yes. You can learn it even if your size of the memory is O of n, even if you can remember only n bits. And one way to do that is by trying all the possibilities. You just try the possibilities one by one, and for each possibility you look on, let's say, the next 2n samples, if it satisfies all of them or not. And if yes, this is probably the right one. If not, this is not the right one. But for that, you need an exponential number of samples. And the question is, if this is the best possible, if you only have O of n bits of memory, can you do with less than an exponential number of samples? Yeah, but this will take exponential time. This. Yeah, Avi was willing to wait exponential time. But in 5, it's not too bad. Exponential 5. The main result that I'm going to talk about is that any algorithm for parity learning requires either a memory of quadratic size or an exponential number of samples. So one of them you must do. Or in other words, if the memory size is less than quadratic, then you need an exponential number of samples. And the constant that I'm able to prove here for the memory size, for here the constant is 20. If your memory is anything smaller than n squared over 20, over any constant larger than 20, 20 plus epsilon, then you need an exponential of samples. The right constant is probably 4. This is the best upper bound. And to do the example that I did before, you need 9 bits of memory to do that. Yes. This is exponential anyway.
There's no trade-off. No, but can you do like...
So you still, it's still exponential.
It's exponential even, there's no trade-off. It's a threshold.
Squared is exponential already.
Yeah.
Even what?
Anything below n squared is
Below n squared over 20, over, let's say 25, any constant larger than 20. So this is the main result. This was conjectured last year by Steinhardt, Valiant, and Wager. And they were the first to ask this question, so a lot of the credit for the result should go to them. I just want to say that previously there was no lower bound for the number of samples, even if the memory size that you allow is n, which is the space that takes you to remember one sample. And this was the case for any learning problem, not only for parity learning. So there was no lower bound, no non-trivial lower bound, even if the memory size was bounded by n or 2n, depending how you define it exactly. What I wanted to say is that this result might be related to learning theory, complexity theory, and cryptography. And I will tell you a little bit about that, not all connections that I know, but a little bit about each. So the result is most related to learning theory. It actually came from learning theory, from the paper that I already mentioned of Steinhardt, Valiant, and Wager from last year. There were several works in learning theory that studied learning under memory constraints. And in particular, there was a paper by Ohad Shamir and the paper that I already mentioned that studied this exact problem of learning under memory constraints. But there are many other papers that these two papers cite that study related problems, learning under constraints of memory, communication, and information. And also they obtain several partial results that they show how they generalize many previous results. So it came from learning theory, and in the language of learning theory, our result shows that there is a concept class that can be efficiently learned if the learner has a quadratic size memory. But if the learner has anything less than quadratic, then the concept class cannot be learned by less than exponential number of samples. In other words, in some cases, learning is infeasible due to memory constraints. Or if you want, good memory is crucial in learning or cognitive processes. And I guess we all know that. We all use a piece of paper or the blackboard when we do math. And luckily, it doesn't have to be our memory. It can be the blackboard. And as you can see in this picture, even if your own memory is bounded, if you use the blackboard, you have the chance to disprove Fermat's last theorem, or to show that the torus is homeomorphic to the sphere, or to or to invent the big omega notation, maybe even in the same formula, all of them. Okay, so what about computational complexity? In computational complexity, time-space trade-offs were studied in many different settings, and in particular, time-space trade-offs were studied for computation of a function f of x1 to xn, let's say by Turing machine or by branching program. Actually, there are two very beautiful lines of research that I want to mention. One that studied the non-uniform case, that is non-uniform model of computation. Actually, the model of computation that is used is branching program, and this is also the model of computation that I'm going to use in this talk, in my work. And this line of research gave an explicit example for a function f, such that any algorithm for f requires either space larger than n to the 1 minus epsilon or time larger than n to the square root of log n over log n, or something like that. Something like n times square root of log n. So this work is by Beam, Giram, and Sachs, but they gave only a constant times n here. And then Aitai was the first in two works. These are actually two works. Aitai was the first to give superlinear lower bound here on the number of on the time under space constraints, and this was improved by Beam, Sachs, Sun, and V. So this is one line of works, and another line of works studied the problem in the uniform model for Turing machines, and this started by a great result of Lance Fortnow in '97. Was improved in many follow-up works. These are only some of them. And this line of works showed that any algorithm for SAT requires either space larger than n to the 1 minus epsilon or time larger than n to the 1 plus delta. And this is in the non-uniform case. Delta is in the uniform case. This is for Turing machine, not for a branching program. And the delta is some constant between 0 and 1 that kept improving. So the best constant is by Ryan Williams. So you can see in these two lines of works that they only get lower bounds of at most n to the 1 plus delta under space constraints. And the question is, what makes it possible for us to get exponential lower bounds under space constraints? And the answer is that the models are different. The model that we consider here is different than the model of in computational complexity. When you talk about a computation of a function f of x1 to xn, you assume that you can always access the inputs x1 to xn. The inputs are always there, they are stored for free, and you can always access them. And in our learning problem, once the learner saw the sample, the equation AT-BT, this equation disappears unless the learner stores it in its own memory. Otherwise, this sample disappears. You cannot access the same sample again. You can always get a new one that will be as good as the old one. It's another sample, another random sample, but you cannot access the exact same sample that you already saw before. So this is the difference. There is also, and this is the difference that we are able to exploit in order to get exponential lower bound. There is also a minor difference that is really minor, that in n means different things in both cases. In our case, it's the sample size, and here it's the input size. But forget about this. This is less important. Okay, I also have an application of the main result to cryptography. And this is for the model of bounded storage cryptography. Now, suppose that Alice and Bob both have a secret key X that was chosen randomly in 0, 1 to the n. It can also be a group of users that have a secret key in 0, 1 to the n. And they want to use it to encrypt, to send encrypted messages. So, of course, one thing that they can do, they can use can use it as a one-time pad, but then they can use it only to encrypt, only to send n encrypted bits, because you cannot use the same bit twice, the same bit of key twice. So I want to suggest here another way that will be secure if the attacker has a bounded size memory. And this is the way. So suppose that Alice wants to encrypt a bit m. What they will do, let's assume that A is a string of n random bits that is known to both Alice and Bob. So we assume that there is a source of random strings that transmits random bits to all parties, and all parties can see this source. If such a source is not available, it's not a big deal. Alice can choose herself the random bits A, n random bits, and send it to Bob. Okay, so now both Alice and Bob know A. Everybody knows A, even the attacker knows A, but this will not be a problem. Both Alice and Bob know X, and therefore they can compute the inner product of A and X, call it B, and use B as a one-time pad to encrypt the bit M. So the encryption is by taking M plus B modulo 2, and then Bob can decrypt. So Alice sends M plus B modulo 2 to Bob. Bob just add B modulo 2 and gets back the encrypted bit M. And you can see that we used a secret key of length n, and the time that it takes to encrypt and decrypt is also n. You need to compute the inner product, or maybe even to send these A bits if such a source is not available. And the claim is that this will be provenly and unconditionally secure for attacker as long as the memory of the attacker is of size at most n squared over 25. And the scheme is used at most an exponential number of times. So as long as this is true, the attacker uses at most n squared over 25 memory bits, and the scheme is used at most an exponential number of times, this is provenly and unconditionally secure.
You
Yes?
secure in the sense that the adversary will not be able to find X, but not in the sense that he will not be able to find some X.
You will see immediately. Okay, so what do I mean by secure? By secure, I mean, so suppose that we are going to use this scheme. By secure, I mean that even after, suppose that there is an attacker that can see everything, can see A1, B1, A2, B2, until ATBT, we know by the main result that the attacker, by just seeing that, cannot figure out what is X. And not only the attacker cannot figure out what is X, the attacker cannot even guess X with exponentially small probability. I didn't tell that before, but this is the main result. You cannot guess X even with exponential. You can guess only with exponentially small probability. And therefore, if the attacker cannot guess X, now there is a new random string AT plus 1 that the attacker can see, but this is not a problem. By the fact that inner product is a strong extractor, the attacker cannot guess BT plus 1 with better than exponentially small advantage. So the attacker, even if the attacker saw all the communication so far, everything, knows everything that happened so far, the attacker will not be able to predict the next bit with better than exponentially small probability. So this is what I mean by secure.
The fact that they can guess with better than exponentially small probability is an easy corollary of the lemma. Right? If they could guess it, they could just try and go over all the options that all the candidates.
That's true, yeah. Yeah, probably, yes. Okay, so this is something that you might try at home even. I don't know. So what is good here is that it keeps improving with technology, because you only need like complexity of n for encryption, decryption. complexity of n, memory of n to store your secret key, but then it's good against attackers of memory n square. So when technology improves, it keeps improving. So this is the application. This falls into the framework of bounded storage cryptography that was started by Maurer in '92, and there were many other works on this subject. But all previous works on bounded storage cryptography assume that the attacker's memory size is at most linear in the time needed for encryption, decryption. So what this work did more or less was they assumed that there is a high rate source of randomness that transmits random bits to all parties, and then you more or less wait until the attacker cannot store all these random bits anymore because its memory is small compared to the number of random bits that are transmitted. And then there is a short secret key that the two parties kind of point on a place from which they start to take random bits to use or something like that, or they can use it as a seed for extractor or something like that. But the main point was that you have to wait until the memory of the attacker is clogged by random bits, and only then you can start decrypting securely. And in our scheme, we need a secret key of size n and time of n for encryption, decryption, and it's good for attacker of memory size n square over 25. Now, I want to say that we need an encryption, decryption time of n per bit. So if you want to encrypt messages of length n, this gives no advantage over previous works. So it's more suitable for cases that you want to encrypt many short messages without keeping track of what you used and what you didn't. Or maybe there are many users that want to encrypt many short messages. So this is one thing. And the other thing that we use, as I said, a secret key of length n, and in previous works, a secret key of length log n was sufficient.
If I already have a secret key of length n, I can just use it as a one-time path for a message of length n.
Yes.
Or any message with
Yes.
length n.
Yes.
So
Yep.
why wouldn't I just do that?
No, because if you want many messages without keeping track of what you did already, if you like, what you are saying is true. If your message is smaller than n, you can use as a one-time pad, and if it's larger, you can do the previous things. This is true if you know in advance that you're going to encrypt one message and you know what would be the length. But what if you want to encrypt now a message of...
Every time I want to encrypt a bit, I use the ith bit of x.
Yes.
And then until I run out of bits in x.
Yes, and then what?
So but that's n messages.
That's n messages, yeah. But then what?
But here, if I have n messages, I already have n squared.
No, here if you have n, you can use this as many times as you want. You can use it cube messages when they are all small. So that's what I'm trying to say here. That this is suitable for situation where the user want to encrypt many short messages and not one long message without keeping track. You think of it as many users want to encrypt, decrypt without even keeping track of.
You can actually probably encrypt and decrypt. So you can do it with matrix multiplication.
If I have more than. That's a good point. Yeah, I didn't think about it, but yeah. Okay, so this is the application to cryptography, and what I want to do now is to tell you what is the computational model that we assume. This is just branching program. If you know what it is, it will be easy. A branching program of length m and width d. So a branching program of length m and width d, it's a directed graph with m times d plus 1 vertices arranged in layers, in m plus 1 layers, where there are d vertices in each layer. And each layer represents a time step. Each vertex in a layer represents a memory state of the learner in that time step. So again, this is the time and this is the memory. And for every vertex in the branching program, we have 2 to the n plus 1 outgoing edges. One for each a, b in 0, 1 to the n times 0, 1. So one for each possible equation. And when, suppose that at this time step, the learner is in this memory state, these edges all are going to the next layer, and they represent the action, to which memory state the learner switches after, if the learner is now in this memory state and the learner reads AB. So if the learner is in this memory state and reads AB, the learner just moves to this memory state. So this is a branching program. And now, when we get samples A1, B1 to AM, BM, these samples define a computation path, what we call a computation path. We start from this vertex that is the only vertex in layer 0. We have a start vertex in layer 0. And we follow the edge A1, B1. We follow the edge A2, B2. We assume that there is exactly one edge labeled for each AB. So we have such an edge. We follow these edges until we get to the last layer. We assume, I still have to tell you what is the output. We assume that in the last layer, each vertex is labeled by some vector in 0, 1 to the n. So we denote it by x hat v for a vertex v. And this is the output of the branching program if it gets to this vertex v. So for each vertex here, there is an output of the branching program if we get to this vertex. So this is the computational model that we assume. And now I can tell you the result. The result is that any branching program of width at most 2 to the n square over 25 can be anything better than 20, larger than 20. But then this constant we say. But anyway, if any branching program of width at most 2 to the n square over 25 and length at most 2 to the n over 25 outputs the correct x with exponentially small probability. So this is the main result.
When x dictates the path.
When what?
When x dictates the path.
Yes, yes.
You just said how the branch program works for any inputs A1, B1, but
so
the inputs will be A1.
The inputs will be as I defined at the beginning. AI is just a random vector, and BI is the inner product of AI and X. So these are the inputs. The inputs are not BI must be the correct BI for every I. And then still, even if you're so log of d is the memory that you use, n square, the number of memory bits that you use. Even if you use n square over 25 memory bits and an exponential time, you still output the correct x with exponentially. You can do that with exponentially small probability. Okay, so let me give you a very high-level proof outline. I hope to give you all like the main ideas of the proof today. Not all details, but at least the main ideas, depending how much we will, how much time we will have. So the main, the high-level outline is that we are going to first define a subclass of branching programs that we call affine branching programs, or ABP, affine branching program. The easier part will be to prove the theorem for affine branching programs. We will show that any affine branching program for parity learning has either width 2 to the omega of n squared, or length 2 to the omega of n. Exactly the theorem for affine branching programs. So this is a simpler model that we can actually prove the theorem for that simpler model. And then the harder part will be to simulate a general branching program by an affine branching program. So this is like a dream scheme for lower bound proving. Find an easier model, prove the lower bound, and then reduce the hard model to the easier model. It rarely works this way, but sometimes it does, and here it doesn't. Now, when I say here that we do a simulation of a general branching program by an affine branching program, you probably think of a polynomial time simulation. No luck. Maybe quasi-polynomial? No. Maybe exponential? Even not exponential. It's probably the worst simulation you have ever seen. The simulation expands the width of the branching program by a factor of 2 to the theta of n squared. Of 2 to the n squared. So it's a really bad simulation. But this is still sufficient because the constant here will be smaller than the constant here. So you have to be very careful. This makes the proof very delicate. This part we will prove with very tight constants. And this will be very important. And this tight will be done. So actually it's very easy to do that if it's very easy to do that with 2 to the theta n square expansion, but with bad constant. But we will improve a little bit over the bad constant, and this will already be enough because this part will be extremely tight. So this is an imprecise high-level description of what is going on. I will give a more precise description in maybe 10-15 minutes, but I hope to show all the ideas of the proof today. Okay, so what's an affine branching program? An affine branching program, intuitively, an affine branching program is a branching program where each vertex v remembers, in some sense, and we will see in what sense in a second, a set of linear equations EV in the variables x1 to xn. And it should satisfy that if the vertex v is reached by the computation path, then all the equations in EV are satisfied. So this is like the first thing that you would try to, if you try to learn X, you would say, okay, I got this equation, I will remember it. I got this equation, I won't remember it because I will wait for the singleton. When the singleton arrives, I will remember it. And then maybe I compute some linear combination of something that I know and only remember the linear combination because it's a singleton or something like that. This is what you would have tried in order to learn. So the equations in EV, if this is V, the equations do not have to appear on this path. They might be weird linear combinations that appear, but they must satisfy that if you reach a vertex, all the equations in EV are satisfied. So this is equations that you remember to be correct. This is the intuition. I have to give a formal definition. Yes?
How hard are you willing to work to get those EVs?
As hard as you want. There is so as long as you follow, as long as you use a branching program of width d and length m, you can do anything that you want. These arrows, these edges, can go to any memory state. I don't restrict it. It can be even, so from layer to layer, you can work as hard as you want.
It's a non-uniform model. It doesn't matter how long it took to create it. What you will prove is that no such model exists. Doesn't matter how as long as the width and length are.
Maybe when you see the formal definition, it will be more clear. And this is more or less the formal definition. One thing is missing that I will show later on. So an affine branching program is a branching program where each vertex v is labeled by a set of linear equations EV that satisfies the following properties. So again, for each v, we label it by a set EV of equations. This is the set of equations that the vertex remembers. And we want two properties. The first is that the start vertex is labeled by the empty set. So originally, we don't remember anything. We don't know which equation is satisfied and which is not. This is the empty set. The second property is that if uv is an edge, for every edge uv in the branching program that is labeled by AB, the set of equations EV is contained in the span of the set of equations EU together with the equation AX equal B. Why? Because if here you remember EU, and here you know that you cross this edge. Since you cross this edge, you know that AX equals B is satisfied. So you know that all these equations are satisfied, and all these equations are satisfied, but you don't know anything. You don't remember anything else. So therefore, we assume that EV is a subset of the span of this equation of EU union with AX equals B. Exactly. That's why it's subset.
Oh, it's a subset of the equation, so it should be a bigger. It's not a subset as a set. The set of solutions is not a subset. The set of solutions is.
This is the set of equations. Actually, in the paper, I wrote it as a set of solutions, and we will switch to this view later on. But what?
Then you switch the direction.
Yeah, then you switch the direction.
So you can forget everything.
You can forget whatever you want. This is important. It will be important for the simulation. And in a way, this is the most general model. I don't know, maybe I was stuck with some bad equations that I want to forget them all and start fresh with waiting for better ones or just remember some of them. So EV can be any subset of the span of EU and AX equals B. And this should be satisfied for every edge in the branching program. And if this is satisfied, it's clear that if the branching program reaches some vertex V, then EV must be satisfied. Why? Because suppose that this is EV and this is V and this is U. To reach V, we have to cross some edge UV. Here we know that EU is satisfied. We know that we cross the edge, so AX equals B is satisfied, and therefore EV must also be satisfied. So you know that if you reached a vertex V by the computation path, then all the equations in EV must be satisfied. So this is an affine branching program, but I still didn't tell you how you give the output of the affine branching program. So you will give the output at random. So the affine branching program finally reaches a vertex V in the last layer. This vertex V has a set EV of equations that this vertex remembers. And we think of it as the vertex doesn't remember anything else, and therefore we just choose a random solution of this set of equations, and this is the output of the branching program. So this is a formal definition. There are other ways to define it. Actually, in the paper, it's defined a little bit different. This is fine.
Maybe confusing some. I mean, even it's possible that EV is a set of n equations that uniquely define an x.
Yes.
But you don't have too many of them. Right?
Yes. Sometimes EV will be the set of all n equations that define x. And then you will surely output the correct x. But if EV is a small set of equation, you will most surely output a wrong x. So our goal will be to show that we are not going to reach a vertex that remembers a lot of equations. That with high probability, we will end up in a vertex that remembers a small set of equations, for which EV will be very small. Okay, so this is an affine branching program, And what I want to show you before the break, I want to show you the proof for affine branching program. It's not a hard proof. Some places were a little bit tricky, but I think that right now it's not really hard to understand, I hope. Okay, so what I'm going to do now is the proof for affine branching program. We want to show that an affine branching program will output the correct x with small probability. So let's assume for a contradiction, or let's assume that we have an affine branching program of length 2 to the epsilon n and width 2 to the epsilon n square. Where think of epsilon as an extremely small constant. It doesn't have to be extremely small, but think of it for this presentation as smaller than all other constants here. So, and we want to show that this branching program cannot output the correct x with high probability. So how do we show it? Okay, first I want some notations. So first I'm going to assume that EV equals the span of EV. So you remember all the span of the linear equations that you remember. I do that just so that I don't have to introduce a new notation for span EV. So just, and it's without loss of generality, of course. You don't. Yeah, think of EV as a subspace of equations. Or you can think of the subspace of solutions, as Zev suggested, and actually we will later on think about it as a subset of solutions. Here it's easier to think about it as a subset of equations. And also let's fix k to be some small constant times n, 1 over 5n. Epsilon is much smaller than 1 over 5 for this presentation. Now, what we will show is that the probability that the computation path reaches any vertex v with dimension of EV larger than k is exponentially small. So the computation path does the computation. Finally, it gets to a vertex. This vertex with probability close to 1 will be a vertex with dimension of EV smaller than k, smaller than 1 over 5n. Only with exponentially small probability, it will be a vertex with a lot of equations, with dimension of equations larger than 1 over 5n. And therefore, now when we take, if the number of equations is at most 1 over 5n, the number of solutions is at least 2 to the 4 over 5n. Is exponential number of solutions. The number of the subspace of solution is of dimension at least 4 over 5n, and therefore our chance to guess the right solution is a very small chance. And therefore we will only guess the right one with exponentially small probability. So this is what we have to show, that the probability that we reach any vertex v with large dimension is exponentially small. And this is what we will show. And first, before I get to show that, I want to assume this without loss of generality. I want to assume without loss of generality that for every vertex in the branching program, the dimension of EV is smaller equal k. Now, I only assume this. Of course, if I assume this at the beginning, then I would be done. But I assume this to prove that the probability to reach dim EV larger equal k, to reach dim EV equals k, is exponentially small. So I will assume that without loss of generality, that for every v in the program, the dimension of EV is smaller equal k. And I want to show you how I can assume that without loss of generality. Why I can assume that for every vertex in the branching program, yes, exactly. So the important thing is that if I look on an edge UV, the dimension of EV can be at most the dimension of EU plus 1. And this is by this rule that I wrote here for reminder. EV is contained in the span of EU and AX equals B. And therefore, the dimension of EV is at most the dimension of EU plus 1. So when I go over the computation path, the dimension can climb by at most 1 in each step. And therefore, to reach V with dimension larger than K, I must first reach V with dimension exactly K, and then I can stop. So I can just remove all the vertices with dimension larger than K from the program and still calculate to reach a vertex with dimension exactly K, and it will be the exact same thing as the probability to get to some vertex with dimension larger than K. So we can just remove from the program all the ones with dimension larger than K. And this is important. It's simple, but it's a crucial point in this proof. Okay, and still, so again, now all the program, all the vertices of the program are vertices with dimension smaller or equal K, but what we need to prove now is not that the program doesn't output the correct output, because this is clear now. What we need to prove is that the probability that we reach to a vertex with dimension exactly K is exponentially small. And the main thing that we will prove is the following claim. Fix one vertex V with dimension equals K. By the way, I wrote here all the things that you need to know. This is the main condition that we had for a affine branching program, and these are the things that you have to remember. EV is the same as span EV, K is 1 over 5n, and for every V we assume that the dimension of EV is smaller than K, smaller or equal K. Now what we want to prove, what I want to prove is that fix one vertex V with dimension of EV equals K. One vertex. Now what I claim is that the probability to reach that particular vertex is 2 to the minus omega n square. It's very, very small. 2 to the minus omega n square. It's crucial that it will be here 2 to the minus omega n square. And this is the power of this proof, this 2 to the minus omega n square. Now, if you have this claim, you do a union bound over all the vertices of the branching program over 2 to the epsilon n square vertices, and you get that the probability to get to any vertex with dimension EV equals K is exponentially small, and this is because you take here epsilon to be smaller than what you will get here. Okay, so this actually completes the proof, except that you need to prove the claim. You need to show that for any vertex V with dimension EV equals K, the probability to get to this vertex is 2 to the minus omega n square. And I will give a sketch of the proof, but it gives the main idea. So let's denote the vertices on the computation path by Z0 to Zm. Z0, Z1, Z2, Z3 to Zm. And let's assume, without loss of generality, that V is in the last layer, just for simplicity. Now we want to measure how much progress we made in reaching V. And we will measure the progress by the dimension of EV intersection with EZI. ZI is the current place that we are on the computation path. We have EZI is the set of equations that we remember. EV is the set of equations that we are aiming to, because we are aiming to the vertex V. And the dimension of the intersection we denote by Ri. So originally Ri is 0 because we remember nothing. EZ0 is the empty set. Finally, if we reach the vertex V, Ri will be equal K because EV will be EZM and the intersection will be EV, which is of dimension k. So if we do reach EV, then if we do reach V, then it will be k, and so it will somehow grow until it gets from 0 to k. Now it's important.
It goes up and down. It doesn't grow.
Yes, it can grow and it goes up and down, but what is important that it cannot grow by more than 1 in each step. And this is for the same reason as before. So this is because EV is contained in span EU union with AX equals B. So you only add one more equation. You can increase Ri by at most 1. So it goes by at most 1 each time. So if it goes from 0 to k, there are k places in which it grew by 1. Now, okay, so we know that Ri plus 1 is smaller than Ri plus 1, smaller or equal. But let's see what's the probability that Ri plus 1 will be equal Ri plus 1. What's the probability that it really increases? And my claim is that this probability is exponentially small. The probability, and this takes maybe a minute or two to see, but the probability that Ri plus 1 will be larger than Ri, I claim that it's smaller than 2 to the minus n minus 2k. And this, it's actually even smaller than that. But this is because in order to Ri plus 1 to be larger than Ri, you need the new equation that you get, Ai plus 1 Ai plus 1 Bi plus 1, you need this sample to be somehow related to Zi and V. If Ai plus 1 Bi plus 1 is kind of orthogonal to both Zi, to both Ezi and Ev, then it will not add anything to the intersection. It must be in the span of Ezi union Ev in order to increase Ri by 1. If it's not related to them in any way, it cannot increase. So it takes maybe a minute to see that, but this is more or less the, this is what happens, and this happens with small probability, exponentially small probability as written here.
What you have to show that if you partition all the linear equations into 2 to the epsilon n, or 2 to the epsilon n squared sets, this is something like...
What are you trying to...
Look in the branching program on vertices, and you look at all the edges that go into them, right? So you have to...
Are you trying to prove this?
I'm trying to understand why it's true, maybe, but
Okay.
to see it, or just looking at all the edges going into one vertex and saying that it has to satisfy, it has to be in the span of many different things. So a typical one, it's just it's not going to get anything or any information.
So I'm thinking about it as an edge that is going out of a vertex.
A very simple case that may illustrate this is just the case that EV is empty, right? And what's the probability that you'll increase it from 0? So the intersection, the dimension of the intersection is 0. What's the probability that it will become 1? Only if the equation sits in EV.
Yes, actually, that's a good point.
The general case is the same.
Yeah, this is a really good point. Suppose that Ezi was empty. If you want, so Ri is of course 0. If you want Ri plus 1 to be 1, you need Ai plus 1 Bi plus 1 to be in the span of Ev. You need the new equation that you get to be in the set of equation Ev in order to increase Ri plus 1 by 1. So this is the easy case, but all cases are more or less the same. You must, in order for this to increase the intersection, you must be able to somehow write it as a linear combination of something here and something here. You must be able to write something here as this plus a linear combination of something here. So this is more or less the argument. But it's okay. If it takes 2 minutes to get that, but it doesn't really matter. That's what we have. That the probability that Ri plus 1 is larger than Ri is exponentially small with like real great bound, 2 to the minus n minus 2k. And now what we do, suppose that Zm, the last place on the path, is V. Then Ri plus 1 larger than Ri must occur k times along the computation path. And for each time, the probability for this to occur was 2 to the minus n minus 2k. Since it's n times, we get to probability of 2 to the minus n minus 2k times k. You still have to take union bound over m to the k places, but m is 2 to the n times epsilon, so this is small compared to this. And I ignored here dependencies, but you don't have here dependencies, but what you do have is that this bound is true even when you condition on all the past and on the vertex that you are currently on. So that's how you get the bound. So I know it's not a full proof, but this is how you get the bound. And it's important that the bound here is really good. It's 2 to the minus n minus 2k times k. The number of subspaces, the number of subspaces of dimension k is less than 2 to the n times k. So you have here 2 to the n. You have here 2 to the n minus 2k times k. This is the probability. It means that this is with minus sign. So with plus sign, this is the bound that you get on the number of spaces, on the number of vertices of dimension k in the branching program. So this is the bound that you get, and it will be important for us that this bound is pretty tight. Okay, so this is a sketch of the proof for the affine branching program. And now let me give you a more precise outline of what is going on in the proof. So again, k is 1 over 5n. What we already showed is that, at least sketched, that in any length 2 to the epsilon n affine branching program for parity learning, the set of all EVs, if you look for every vertex V on the set EV, it contains almost all k-dimensional subspaces. If you just look on EV for every vertex V, you have many, many subspaces. It will contain almost all k-dimensional subspaces, and by almost all I don't mean like 1 minus epsilon. I mean that it will be 2 to the n minus 2k times k out of 2 to the n times k. So the logarithm will be almost all. So it's not exactly almost all. So this is one thing that we already sketched. And what we will do, we will show how to simulate a general branching program by an affine branching program, where when we look on all the vertices V for each of them on the subspace, so these subspaces will we will only have a small number of subspaces of dimension k. And by small here, I mean more or less 2 to the half n times k, or 2 to the half n plus epsilon times k. So it will be small compared to this. It will not be really small. It will be still 2 to the omega n square, but compared to the bound that we have here, it will be relatively small. So this is what we will do, and see, I already sketched that. After the break, I will sketch this proof. I will not be able to give all details, but I will sketch the simulation of a general branching program by an affine branching program.
All right.
So as I said, what I will forget about this. This will be later. So what I want to do now is to show how to do the simulation of a general branching program by an affine branching program. And first I want to introduce some notations. Maybe I will write it here. So by A N, I'm going to denote the set of all affine subspaces of 0, 1 to the n. For an affine subspace W in AN, I'm going to denote by UW the uniform distribution over W. So this is a notation. Now I'm going to do some notations for affine branching program, and this is to switch to what we discussed before, to switch to this view of an affine branching program when you label each vertex by the set of solutions rather than the set of equations. So for every vertex V in an affine branching program, so this is a vertex V, we denote by W of V the set of solutions of EV, of the set of equations EV. So this is WV. And the dimension of WV is 2 minus the dimension of EV. Okay, is n minus the dimension of EV, sorry. Okay, and I want another notation is the following. If E is an edge in an affine branching program that is labeled by AB, then I'm going to denote by W of E the set of solutions of EU union with the equations AX equals B. So this is what you know if you crossed the edge E. If you cross the edge E, you know EU and you know AX equals B. So the set of solution of these equations. And this is the same as the intersection of the set of solution WU intersected with the set of solution of AX equals B. And now actually we can write the main condition of an affine branching program in this language, that for every UV, for every edge UV, W of E is contained in W of V. This is an affine branching program. W of E, the set of solution of E, is contained in the set of solution of V, because you can forget. You know that you are in, that X is in WE, and now you can forget and say, okay, we are in WV. WV is they are all affine subspaces. We all live in AN, A of N. Okay, so these are just notations. So when we have an affine branching program, we can define, maybe I will write this also here as a definition. The distribution of X conditioned on V is the distribution of the input X conditioned on the event that the computation path reached the vertex V.
This is a affine branching program or any branch?
So for any branching program, you can define that. Okay, yeah, for any branching program, let's define the Px conditioned on V to be the distribution of X conditioned on V. For an affine branching program, we know that this distribution, the support of this distribution is on W of V.
In fact,
It's what?
it's U. W.
It's not. In an affine branching program, you don't know that.
No, you don't know.
You only know that the right solution is contained, for sure contained in W of V. But you predicted the future, the near future. Now we're going to talk about an accurate affine branching program. So what is an accurate affine branching program? An affine branching program is an affine branching program such that for any vertex V, the distribution of X conditioned on V is epsilon close to the uniform distribution over W of V. So originally we only know that the support of this is in W of V, but it will be accurate if it's really close. Our epsilon will always be exponential. This is epsilon accurate affine branching program. For this presentation, I assume that it is true for every V. In reality, we need in the definition in the paper, we need to have almost any V, or actually we need to have it with expectation over V, where the expectation is over the distribution that you get from the computation path. So it's a little bit more complicated, but for now assume that this is true for every vertex V of the affine branching program, and this is called an accurate affine branching program. If this is satisfied, then this is what you thought. But in general, affine branching program can be anything, not anything, but anything that the support of this is W of V. But this is accurate branching program, and actually in our simulation, we will simulate the general branching program by an epsilon accurate affine branching program. And the simulation will be by induction. So the induction, these are the layers of the general branching program. We will work layer by layer on the general affine branching program, and layer by layer we will try to switch it to simulate it by an accurate affine branching program. So suppose
The induction
this will be for the induction for doing the induction.
And epsilon will be exponentially small, so you can accumulate it over the exponential.
Yes, but it won't be that trivial. You will have to be very careful. Okay, so I plan to talk about it later. Okay, let's just do that. So we're going to do that by induction over the layers. We have to be very, very careful in the induction to accumulate the epsilons additively. And you cannot even introduce a small constant. So if here you have a small epsilon, you cannot say, okay, here we will have 1.1 that epsilon, because you do this induction an exponential number of times. So you have to only add additive errors, and this is a pain. But it's only technicalities. It makes everything much more complicated, but it's only technicalities, and I'm not going to really get into that here because I just want to show the main ideas. So anyway, so we have, suppose that we already simulated all this all these layers until layer T by an accurate affine branching program, and we want to simulate the next layer. So what does it mean that we simulated everything by an accurate affine branching program? So we already replaced these layers by an accurate affine branching program, and for each vertex u here, we know that this is satisfied.
Yeah, you didn't define simulation yet.
I didn't, and I won't. But
so, at least intuitively, what will happen for every vertex of the original branching program? It will be split, or it will be simulated by many.
Subspaces that approximate. Yeah, you will see that. You will see that.
Yes, what you said.
I'm not going to define simulation, but you will see.
But okay, intuitively it makes sense. You split your memory by each memory state. Yeah, so you can define
yeah, but I have only 40 minutes. If I do this definition, I waste 15 minutes.
No, I think that's an intuition. A simulation of a memory state is by...
But you will see that, you will see that.
But the same is also costly.
Now you're wasting more time arguing.
It's fun to argue. What do you mean? With Ran in particular.
Okay, anyway, so let me remind you, we assume that we already simulated all this part by an accurate affine branching program, which means that for every vertex u here, we already have this condition. Okay, so for every vertex u here, in this part, we already defined what is EU, and we already defined what is WU, and we have this condition. And what I want to do is to show how to simulate the next layer, and then it will, I hope it will be clear. I will show only the main ideas, but I hope it will be clear what's a simulation at all. Okay, so as I said, we assume that for every vertex U in layer T, we have this condition with epsilon that is exponentially small. So what I'm going to assume for this presentation is that is equality. You can't really do that, as I tried to explain before. You can't really assume that this is an equality, because then you might multiply the previous error by 2, which will remain 0, but of course will not work in the induction. So actually in this presentation, this is what will happen. But with some more technicalities, you can make sure that all errors are additive. So for this presentation, let's assume that this is true. So for every vertex here in layer T, and now we want to kind of continue the induction, to do the induction, and to get to get an accurate branching program also for layer T plus 1. So let's take one vertex V in layer T plus 1.
In which branching program, the original or the?
In the original. So what happens is that up to here we already changed the branching program, and from here it's already it's still the original random, the original ABP, and we just change it layer by layer.
So this one property of the simulation you have to say is that the edges of the previous branching program manifest themselves already.
Yes.
Yeah.
So
you already know the edges. You just replace the vertices.
Okay, so let's take one vertex V in the next layer, and this vertex have many edges going into it from the previous layer. Okay? So when you have all these edges going into it, you can write the distribution P of X conditioned on V as the sum on all the vertices all the edges E equals UV, all the edges going into the vertex V of some coefficient PE times the uniform distribution over W of E, where some PE is 1. So PE is just the probability to cross the edge E conditioned on arriving to V. So again, to the vertex V. But it's not so important what is this definition. So let me explain. We want to see what is the distribution of X conditioned on arriving to V. So if we arrived the vertex V, we must have crossed one of these edges. So we sum over all these edges. For each edge, we have some coefficient, which is the probability that we crossed that edge if we arrived to V. And this is the distribution of X conditioned that we crossed that edge. The uniform distribution over W of E. And this is true because of this assumption that here we are at the uniform distribution over W of U, and then since we crossed edge, we have the uniform distribution over WE.
Because it's a bunch of programs, so these are disjoint events that they use the different views from which you're coming from are disjoint events.
Yes, we arrive V only on one edge. So either on this edge or this or one of them, and therefore this is the formula. This is a formula for the probability, the distribution of X conditioned on the event that we arrived, that we reached the vertex V. And this is, it's not even important what is this formula. It's important that it's a linear combination of uniform distributions over affine subspaces. That's it. That's what is important. Some linear, not linear, convex combination. Some PE must be 1. Convex combination of uniform distribution over affine subspaces. And this is what we know so far about the distribution of X conditioned on V, and we will see what we are going to do with that in order to turn it into an accurate affine branching program.
It's kind of like all the information from the beginning up until there is all sort of summarized in the UWEs.
Yes. Yes.
You don't need anything else before that. That's it.
Yes, exactly. The induction already took care of everything here. And the only thing I'm going to use is this. That I assumed. I remove the epsilon and assume that it's accurate.
Once you reach the vertex, it's like sampling a new X from the subspace.
That's the intuition. That's the intuition. Yeah, that's the intuition. And again, I want to say that you have to be very careful about the errors. But for this presentation, that's what I have. So some convex combination of uniform distribution over subspaces. So now the next step is inspired by Microsoft PowerPoint. Naturally, yeah. So what we are going to do, as Avi said, we are going to take V and split it into many other vertices that I call ungrouping. But then we will also do regrouping. You will see why. So first, okay, so what we need in an accurate affine branching program, we need each vertex to satisfy something like this, not something like this. So what can you do? You can do ungrouping. What do I mean by ungrouping? You take this vertex V, you change it into many vertices, one vertex for each edge. Or you can do a little bit better, and not one vertex for each edge. You can do one vertex for each W of E. Maybe there are several edges that share the same W of E. So you have one vertex for each W of E. So you have here W1, W2, to WL, many affine subspaces, and you have one vertex for each of them. And each of them you connect to the next layers of the branching program as if they were V, the same as V. You just splitted the vertex V to many different vertices. So now for each one of them takes its share in the distribution, and you have this. You kind of remove the sum and the linear combination, and you have uniform distribution. One affine subspace, which is exactly what you need. But what's the problem? The problem.
Like remembering everything that you saw.
Yes, more or less, you remember everything that you saw so far, and very soon, you will explode and you will get all the affine subspaces in AN. So this is a problem. So what we do, we read the next line in Microsoft Python, and we do regrouping. What is regrouping? So maybe I will, maybe I will leave it for now. So what is regrouping? So this is the original V that was splitted to, this is the original V that was splitted to many vertices, W1 to WL. What I want to do is to partition them into groups. And these groups will have to satisfy two conditions.
So just before you say the condition, a good example will be two affine subspaces that differ only in one equation and the bit, the right-hand side bit. Well, you can merge two affine subspaces. That
Yes.
will be a simple example of what the
Yes. So.
It's the larger one.
No,
Okay. Let me tell what I want from this.
you
Not
two affine
like
subspaces that just differ in the right-hand side of one equation. You can take the you can remove this equation.
I think I need to first say what the regrouping should satisfy before talking about examples. Okay, so we add the W1 to WL. We want to group them into sets. What do we expect from this regrouping? So for each set here, we will have another affine subspace W. This affine subspace and this set should satisfy two conditions. The first is that each Wi in this set, each Wi is contained in the subspace W. And the second is that if you take the weighted linear combination of the uniform distribution over all this, you get roughly UW. So UW is roughly the sum on UWI in the set. I is in the first set. Times some weight, the relative weight of this in the set that should actually be P1 over some Pi on all the ones in the set. So this is just the weighted sum that corresponds to this set, and this should be really close to UW. And if you do that, if you find such a W, such a set of WIs and such a W such that this weighted linear combination is close to UW, you can just take all vertices in this set and replace them by one vertex that is labeled by W. That's what you can do. So you take all these vertices in this particular set and replace them by one vertex that is labeled by W. Why you can do that? So by the condition of an affine branching program, you can always increase the set of solutions. So if you go from Wi to W, it's fine because W contains Wi. So you still remains an affine branching program. And second, when you replace the weighted sum by UW, you didn't change the distribution by much. So you added an error, but a relatively small error. So this is what you should do. And you should do that for all, if you kind of manage to partition all your vertices into different groups and each of them to replace, and the total number of groups will be relatively small, you are fine. So this will be the strategy. And so Avi already gave an example for when it's exactly perfect. If you have one affine subspace and another affine subspace that differ exactly by one equation, only by the free bit of one equation, you can just replace the two of them by one affine subspace that contains exactly all of the two of them. And this is exact. You don't have error here at all. But sometimes you have many different subspaces that somehow all together give you the uniform distribution over a larger subspace. Maybe exactly the uniform distribution, maybe roughly the uniform distribution, and they're all contained in this subset. Then you can take all of them and replace by one vertex for all of them. Okay, so this is the strategy. This is what we want to do. The regrouping. But how do we do that? How do we manage to do this regrouping? And this is this lemma that I started to write. I didn't finish writing it, almost finished. So the lemma says, take any random variable W on AN. This random variable is what is written there. With probability PE, it gets the value W of E. It's just the distribution over all the edges that go to V. So again, this will be, that's how we will use it. So we think of this WE as a random variable. WE is a random variable in AN that you get you get the value WE with probability PE. So, but the lemma is general. Take any variable over AN. So it's a random variable that the values that it gets is affine subspaces of 0, 1 to the n. Then there exists a partial function sigma from AN to AN. This partial function will give you the regrouping. This will be the regrouping function. What is the partial function? So if this is AN, the function is from AN to AN. This is also AN. The function takes several values into one value, and all the values that go into one value will be one group. Okay, so sigma is the regrouping function. All the values that go into one value of AN will be one group. It's a partial function. It will not be completely defined over everything, but it will almost be defined over everything, such that the following 4 conditions are satisfied. I only had time to write 3 of them so far, but we will write the 4th one.
But we should think about W as a low entropy random variable. It has to be supported on much less than 2 to the n squared.
No. W is supported over everything. W is anything that you want. Anything.
We will use it for.
No. Not necessarily.
Not because we know. I mean, in that.
After n steps, you don't know anything.
No, I'm just wondering. Don't you know that? I mean, you anyway prove it. You prove that the width does never exceeds 2 to the n squared over 25. So
Okay,
you
okay.
know about on the end.
Okay, you are right. Yeah,
And
you know,
have to
you're
use
right.
it also.
No, I don't.
Or maybe not for this lemma, but eventually you have to use it for the induction, right? You have to prove it at every layer that it's
I
actually
already
any
used it
parameter.
for the affine branching program. The bound that I had on the affine branching program used the width. But this lemma has no condition. W is anything that you want. That's
Very crazy distribution.
crazy distribution over everything,
But
even.
somehow it seems that because we arrive to somewhere, we are remembering something that we should be not over some arbitrary distribution, but over something very structured. And you don't take it into.
I don't. So this lemma is general. I use it for something that is like sparser than all, but the lemma is for everything.
Okay, maybe let's see the lemma.
What?
You should see the lemma.
Yeah, I'm trying. Okay, so the lemma says take any random variable over an. There exists a partial function, sigma from an to n. I'm just trying to explain. This is the regrouping function. All the values that go to the same value here, all the values here that go to the same value here, are the group that are going to be regrouped for one value here, such that 4 conditions are satisfied. The first condition is not very important. It says that the probability over W, that W is in the domain of sigma, is that W is not in the domain of sigma is exponentially small. There is a small probability that sigma was not defined. Forget this and forget this. So this is just to take care of the fact that it's a partial function. The second condition is one of the conditions that we required from our our regrouping is this condition. This condition. For any W in the domain of sigma, W is contained in sigma of W. We are going to replace W by the representative of the group. So it will better be contained. This is a very important requirement that we need to be satisfied. The first condition is that for any S in the image of sigma, for any representative of the group, if you take the expectation over W conditioned on the event that sigma of W equals S, you get roughly the uniform distribution over S. So this is this condition. This is this condition, more or less. So we are going to take all the W's such that sigma of W equals S, all the elements in AN that go to the same S, and group them together. And if we want to group them together and we want it to be an accurate branching program, we want this to be close to US.
So do you need 2 or is 3 or how many?
No, 3 is not enough. We want it to be affine branching program. So this is close. This is not equality. If it was equality, you are right. But if it's close, it means that maybe some of them are not contained in S, and we need to make sure that it's an affine branching program because the bound that we had is for an affine branching program.
So
but you're right that it's close.
the identity map, of course, satisfies this, but you want to gain something. You want to
This is
Yes.
so 4.
This is going to be 4. And 4, we have, okay, so I want to have a little bit of additional complication, and maybe I can write 4 first. Okay, so I want an additional complication. I have a parameter R that can be anything larger than n over 2. And for every R, this will be satisfied. I still didn't write R anywhere here, but I will write it now. Think of R as n times half plus epsilon, a little bit larger than half n. So for any R, okay, so this will be epsilon clause, where epsilon is 2 to the minus R minus n over 2. So epsilon is exponential small, but depending on R. So if you take R to be a little bit more than n over 2, you are fine. And the fourth condition will be that for any k, there are at most 2 to the k times R, 2 to the k times R elements S in the image of sigma with dimension k. With dimension of S with dimension 2 to the with dimension n minus k. N minus k because I want to, because here I talked about a set of equations. Here I talked about set of equations, and here I talked about set of solutions. So I want to match it. So the fourth condition is very important to bound the size of the branching program, the width of the branching program. It says that for any k, there are at most 2 to the k times R elements in the image of sigma such that their dimension is n minus k. Dimension n minus k corresponds to set of equations of dimension k. So think of R as close to n over 2. We get here that the number of subspaces with dimension, the number of subspaces EV, where EV is of dimension k, is 2 to the k times R, where R is roughly n over 2, or n times half plus epsilon. So when you compare this to the bound that we had here, you see that this is larger, where k is small enough.
R times k to match it, yeah.
R times k, yeah. So you see that this is larger. So the lower bound that we proved is better than the expansion that we have in the width of the branching program, and this what makes it work. So this is very important, that we are only going to get a relatively small number of elements S with small dimension, with okay, so this is for any k. For any k, with large dimension, actually, when you talk about the set of solutions. With small dimension when you talk about a set of equations. So this is the lemma. So again, it's not so important what are the exact expressions, just this guarantees that we will have an affine branching program. This guarantees that it will be an accurate branching program. And this guarantees that the width will be smaller, will be large but smaller than the width that we can work with. So these are the four conditions. Okay? Okay, so this is the lemma. Again, this is less important. So yeah, I only have 10 minutes, so I won't be able to show the proof of the lemma. Only give you some hints. So again, when we have this lemma, we take this this V, we ungroup and then regroup using this lemma and continue by induction until we go layer by layer on all the layers of the branching program and turn it into an accurate affine branching program, and we are done. So this lemma is kind of very important. Okay, so maybe I will even show the main ideas of proving this lemma, although I'm not sure, I don't have much time. First, sometimes we are very lucky, and just when you look on all the convex combination that we have, it just gives something close to uniform on the whole space. Maybe we got lucky and we can remove everything and replace by just the whole space. And there is a simple condition of when it happens. So for any r larger than n over 2, and for any random variable w over an, this is exactly as before, assume that for every a, b in 0, 1 to the n times 0, 1, for every equation ab, for every ab, the probability over w that for every x in w ax equals b is smaller or equal to the minus r. Suppose that this is true, that for any ab that you take, if you take a random w according to your distribution, the probability that all the x's in w satisfy ax equals b is very small. So for every AB, it will not be orthogonal to too many of the subspaces. Only with probability 2 to the minus r, you will have that the equation AB is kind of orthogonal to the subspace W that you have. If you have this condition,
it's like being an epsilon bias set, 2 to the minus r bias distribution. Any linear equation holds.
yes. Okay, so this is over, it's not over it's over W,
Right.
not over U, some UW, not over expectation of WUW. Okay? Anyway, this is a condition. If this is satisfied, then the expectation of UW, the linear combination UW over all W, this is the linear combination that we work with, this is very close to the uniform distribution over everything. And how close? It will be 2 to the minus r over 2 to the minus r minus n over 2, close. So this is a condition that guarantees that we are close to the uniform distribution. The way to prove it is it's an exercise. It's just a simple Fourier analysis will give that. So the Fourier coefficients of this distribution are exactly these expressions. These expressions. The probability.
N over 2 comes from moving between L2 and L1.
Yes, yes, the Cauchy parts. So this is an exercise. I will not do that, but again, what it says that the important is the lemma, not the proof is easy by Fourier analysis. So we will not do that. The important is that this is a condition when we can take everything and replace by one element. And the condition is that for any AB, the probability over W that all the elements in W satisfy AB is smaller than 2 to the minus R. And now I'm going to tell you more or less how the proof of the main lemma goes. Actually, I only have 5 minutes, but I will be able to give the main idea without the details. So what we're going to do in order to prove the main lemma, this regrouping lemma, so we are going to do it by iterations. We are going to find one element S and match to S all the... okay, let's do that maybe here. So we are going to find one element S in AN, and we are going to match to it by sigma all the elements W such that W is are contained in S. This is also AN. I'm going to describe sigma from AN to AN. We are going to work by iterations. We are going to find one S that will satisfy, okay, we are going to take an S, we will somehow find it, and we are going to match to it all the elements that are contained in it, all the W that are contained in it, and we will choose such an S that satisfy both the second condition, actually that satisfies several things, but in particular the second condition and the third condition. So we will have the two conditions that we need for accurate branching program. And another property that it will satisfy, that the probability to be here will be relatively large. So, but forget about it for now. So we're going to find one S and match everything that is contained in it to it. I didn't say how to find this S. Now we are going to remove all this from the system, all the ones that are already matched from the system, and we are going to find another S and match to it everything that is contained from it to it that was still not matched. And so on, we are going to continue enough times until we cover the entire space. So we only need to show how to find this S that will satisfy all the good properties that you need. And what we are going to do is the following. Either we are lucky and this is satisfied, and then we will take S to be the entire space and match everything to it. If this is satisfied, this is great. Or this is not satisfied. And then what we're going to do? We are going to, yes, so if this is not satisfied, it's not true that for every A and B this is satisfied. There is A and B that for which is not satisfied, for which it's not satisfied. So for this A and B, this probability is larger than 2 to the minus R. So we just focus on the part of the space that satisfy AX equal B, and on the W's that satisfy A of X equal B. It happens with probability 2 to the minus R, so it's not such a small probability. And there we continue by induction until after kind of k iterations we get to a space S that will, at some point we will get to a space S that satisfies it. And since it satisfies it, it automatically will satisfy 2 and 3 As for 4, we will use this, that at each step we reduce the probability by a factor of 2 to the minus r. So if we end up by a subspace of dimension n minus k, then the probability is larger than 2 to the minus kr, therefore it cannot happen more than 2 to the kr times. So this is, of course, without the details, but, sorry?
You find all the W's for which the whole W is consistent with this equation. There are good probability for this stuff, for those W's. Why don't we just...
Need it to be uniform.
Okay, let me repeat this. Either this is already satisfied for every A and B. Then we are uniform over everything. We can take W and replace everything by the whole subspace. This is great. If not, there is A and B such that this condition is not satisfied, which means that for that A and B, this condition is satisfied. It's larger than 2 to the minus r. So take all the W's that satisfy this condition, that are kind of orthogonal to Ax equals B. That all the W's such that for every element of W, Ax equal B. For that A and B. It happens with this probability, and when you do that, you reduce the dimension by 1, because you look on all the places that satisfy the equation equal B. This is a linear equation, which practically means that you reduce the dimension by 1. So if you reduce the dimension by 1, you can continue by induction. So this is the main idea. Of course, this is not without it. No, Ax equal B, you just now concentrate on all the W's. You add a random variable W over AN. You now just focus on all the W's that satisfy this equation, Ax equal B. And you can think of it as living in not in AN, but AN minus 1.
So those will be like the cloud of W's, and the S will be the union, but...
Okay, so this, you just reduce the dimension by 1 for now, and now you continue to do that. Either now it's the uniform distribution over everything.
What S will be, but S will be exactly the sequence of it. I mean, you are accumulating.
This S?
S is the union of everything, but...
Everything that was consistent with the equations that you collected. You collect these pairs A and B, and this will...
So I think of S as the set of solutions, and then S is just the intersection of all the... Right. Yes, you're right. What? Yeah.
If you are describing the affine subspace of equations, it's just a set of A.
So when you do... Okay, let me try. There is a confusion here between the set of the affine subspace that satisfies the equation and the set of equations. You can think of each of them. So if you think of it as set of equations, then yes, you take this A, B, and you add it to the set of equation and continue by induction. And this way you collect the set of equations, and the set of solutions will be S. But maybe for me it's easier to think of it as the set of solutions for this equation. The set of solution for this equation, Ax equal B, is an affine subspace of dimension n minus 1. So if you reduce the dimension by 1, you can continue by induction. You do induction over n. And you reduce the dimension by 1, and the probability was 2 to the minus r. So after you continue many steps, at some point you will end up with uniform distribution, right? If not, then when you get 1 to singleton, you will end up with uniform distribution. So at some point you end up with distribution that is close to uniform, and then you stop. And you take that, and you define it as your S. And the fact that you kind of the probability decreases by 2 to the minus r in each step means that you will get, if S is of dimension n minus k, you got to S with probability 2 to the minus r times k. So this is the probability. This is a small probability, but not too small. It can only happen 2 to the rk times. If you get to S with such a small probability, and S is of dimension n minus k, the total subspaces of dimension n minus k that you will finally get will be 2 to the r times k. So I know I didn't show this in details, but this is just to give you the idea of how the proof works. I think that these are all the ideas, but not the details.
Does it seem necessary that you need this exponential?
I think so. But I'm not sure.
This last regrouping step looks somewhat similar, or maybe I didn't understand it properly.
The Roth theorem and the three-term arithmetic.
Yes. Yes.
For what?
The proof of this is the increment argument in the proof of that large subsets contain, of the integers, let's say, contain three-term arithmetic progressions.
Okay.
I mean, if you look at so this Roth theorem is a famous theorem for which, followed by Semerelli and so on. But if you, over the integers is a bit more, I don't know, complicated, and the details are messy. But if you look at the Shulam proof that you replace the integers by f3 to the n, you just want to say that then subsets of f3 to the n contain a line, but then contain actually a full line which is of length 3. Then the argument uses Fourier analysis in exactly the same way. So it's inspired by Roth, it's just simpler technically, and it's exactly like this. Either you have a Fourier coefficient, either all Fourier coefficients are small, this is your uniform case. In the uniform case, the probability that if your set is not the whole thing, but if all the Fourier coefficients are small, then the probability that it contains a line is like it is in the uniform distribution. And if not, there's some Fourier coefficient which is biased.
And then you restrict.
And you remove, you induct, you go down one dimension, you
Okay.
gain something like it.
Okay.
But
And
you gain in
the R. This is why you cannot go too much.
No,
This is
you gain in the dimension.
Yeah.
You reduce
but
from n.
also you cannot continue it too many times
Yes,
the
because of
parameter R,
2 minus r.
the parameter R. And also there is a parameter by how the bias. You balance the bias like in RAM. I mean, it's a different problem and different. But you can tolerate some bias as RAM does here, and it manifests in the error. That will tell you how much you deviate when you calculate the number of arithmetic progressions from uniform form, just a small bias space, and you just want to guarantee that you have enough for your one. That's one side. The other side is will not happen too many times. It's what in it first, because you want the width. So that's the balance. In spirit, it's very similar. The condition looks almost like
Maybe, I don't know.